All right, all. So here is where differential equations is going to meet up with linear algebra. So we're doing this from the linear algebra perspective today, but what we're going to actually be doing is solving some differential equations. So in order to get moving forward, I'm going to need you to recall a couple of things. And one of those is going to be from Calc 1. The thing I need you to recall from Calc 1 is that when we differentiate with respect to x, e to the kx, that we get k times e to the kx, right? That's just a straightforward chain rule problem. I also need you to recall a Calc 2 thing. And the Calc 2 thing I need you to recall is that e to the x is given by a power series that's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, and so on, right? So there's another way to write this, which is just to write it out in sum notation. So we're going to sum from n equals 0 to infinity of x to the n over n factorial. Okay, I need these two facts to kind of move forward. And now, if you're in the differential equations class, this is going to feel familiar. If you're not in the differential equations class, we're going to solve our first differential equation. So let's solve our first DE. So we're going to look for a function y that has the property that y's derivative is a constant times the function we started with. So I'm hopeful that this stirs up some memories here. It should stir up some memories from about 10 seconds ago when we said, here's a function that I can differentiate, and it just kicks a k, right? So this is solved by y is some constant times e to the kx. That constant, I'm going to put a lowercase a here. In differential equations, we tend to use a uppercase a for our constant, but I don't want you to think it's a maintenance. It's just a scalar. So this is my thought about how I might find a solution, right? Okay, great. Now let's solve our second differential equation. And this one is going to be new even for folks taking DE, right? So our second differential equation is going to look something like, I want to find a function, but this function is going to be a vector. So I've got a vector valued function. Students who have had Calc 3, this is like one of our parametric curves or something, right? It's a vector valued function. And I want du dt to be equal to a matrix A that's set times my vector u. And I'm thinking to myself, hey, self, that ought to follow the exact same pattern as up here. I ought to be able to just do, not y, but u ought to be e to the at. But categorically, I've got a problem here because I don't actually know what category of thing this is. I'm going to put in here u of 0. That's going to kind of act like our constant out front here. Now, I should probably convince you that this is actually the solution you get. So the way I'm going to convince you that this is actually the solution you ought to get is I'm going to look at e to the at, right? And I'm going to actually kind of do a little calculation for how I might arrive at e to the at. So I'm going to think to myself this. I'm going to think, all right, I want to differentiate with respect to t, e to the at, times my constant. U of 0 is a constant vector, so that's not really going to contribute here, right? So I'm going to have the derivative with respect to t, and I ought to be writing down e to the at. So I'm going to take at and plug that in for x's in my power series, right? So I'm going to get, this 1 is going to be a little problematic for me. What that really represents, though, is an x to the 0 power over 0 factorial. This x represents x to the 1 over 1 factorial, right? So when I plug in at here, I'm going to get at raised to the 0 power. When you take the 0 power of a matrix, that's going to be an identity matrix. And then we're going to get plus at to the first over 1 factorial plus 1 over 2 factorial times a squared t squared plus 1 over 3 factorial a cubed t cubed, and kind of so forth, right? And then I'm going to have my little u of 0 out back here. Then I'm going to think about, okay, if I differentiate with respect to t, I is not changing with respect to t, so that's going to give me the 0 matrix. This 0 is a matrix, not a scalar. Then I'm going to get at. Well, the derivative of at is going to be a times t to the 1 lower power, right? So I'm going to get a t to the 0 here. And then I'm going to add to this. I'm going to get 1 over 2 factorial, right? And I've got a squared. And then I've got times 2t. Notice the 2 here and the 2 there cancel. You guys on board with that? Then I'm going to get a plus 1 over 3 factorial a cubed times 3t squared. And then I'm going to get a bunch more terms that look kind of like this. And this whole thing's going to be times u of 0, right? Then if I look at this, I'm going to notice that this 3 here is going to cancel with that 3 factorial and leave me a 2 factorial. The 4 in the next term is going to cancel with the 4 factorial and leave me with a 3 factorial. Then I can notice that everything is basically 1a long from what I just had. So if I factor an a out of this, I'm going to be left with 0 plus I plus at plus a squared t squared over 2 factorial plus a cubed t cubed over 3 factorial. Oops. I needed my dots inside there. And then I've got my u of 0 out here. So what's the deal with u of 0? Well, when I think about what is this categorically, right? I'm looking at adding all these things up. The identity is, let's say A is an n by n matrix, just for kicks, right? So I'm going to go in here and add some dimensionality. This is a to the 0 power. That's going to be an n by n matrix. This is an n by n matrix times a scalar. This is a scalar, and an n by n matrix in the middle. Again here, scalars on both sides, n by n matrix in the middle. So all told, this thing here is an n by n matrix, right? Like, it's actually e to the at if we're going to call it something. But that's an n by n matrix. And that can't be the derivative of my vector function, right? Because that's a matrix, and the derivative of a vector function is going to be a vector. So this vector here, right, is an n by 1 vector. And when I do this multiplication, the whole thing is going to end up being an n by 1 vector. And then the categories match, and I'm good to go. Cool? So I've shown that it satisfies the differential equation, and I've shown that it's the right category of thing. So, awesome. This is basically me done with these. But I'm going to have some matrices in which I can actually calculate e to the at, other than just like writing down the power series, right? So in our next video, we're going to talk about some matrices for which I can actually calculate that e to the at. For right now, I just want you to know that that's the solution that we should be arriving at. Thanks for watching. Catch you on the next one.